For over a century, driving has relied on controlled violence. Inside a traditional engine, thousands of tiny controlled explosions fire every minute, shoving heavy metal pistons up and down and grinding steel gears together to force the wheels to turn. Step into an electric vehicle, and that mechanical violence is gone. There is no engine oil, no fuel tank, and no exhaust, just silence when you press the pedal. How does a silent stationary battery generate enough force to launch a 2-ton machine down the highway faster than a sports car? To understand this engineering, we have to look past the physical flow of liquid fuel. Instead, we need to trace the invisible, linear journey of a single electron as it travels through the car. Tracing this specific energy pathway reveals an elegantly logical, highly efficient system. The journey begins at the external charging port. This is the bridge where stationary electricity from the power grid enters the vehicle's mobile ecosystem. Power enters in two ways. Alternating current, or AC charging, provides a steady flow for home use. Direct current, or DC fast charging, provides a high volume of energy for rapid top-ups on the highway. The onboard charger routes this electricity into the vehicle's core, the lithium-ion battery pack spread across the floor pan. This storage is measured in kilowatt-hours. There is a direct mathematical link. A larger battery vault means a further driving range. The battery pack acts as a massive vault of potential energy that dictates the physical geographic limits of the car's journey. Storing this much raw energy requires strict governance before that electricity can be safely moved. The Battery Management System, or BMS, serves as the digital brain of the battery. It monitors the voltage, the charge levels, and stability of every individual cell. If those cells heat up, the BMS triggers the liquid cooling system. Coolant pumps around the battery structure to pull heat away and prevent damage. Once ready to move, energy faces a technical hurdle. The battery outputs direct current, a flat line of power, but the motor requires an oscillating alternating current. The inverter acts as the translator, converting that flat line into the rhythmic wave the motor needs. Without these management and translation layers, the energy in the battery would be entirely useless to the wheels. Now converted into AC power, the electricity leaves the inverter and hits its target, the electric motor. The motor converts that electrical flow into mechanical rotation. Because there is no combustion delay, the motor produces instant torque. A vehicle controller and a single-speed transmission deliver this power to the wheels smoothly, removing the need for shifting gears. But the pathway doesn't end at the tires. When you lift your foot off the accelerator, the energy journey continues. This is regenerative braking. The motor runs in reverse, acting as a generator to capture the car's momentum and push electricity back into the battery. Regenerative braking makes the vehicle a self-replenishing energy loop, capturing momentum that would otherwise be lost to heat. Zooming out, we see the entire system working in harmony, the battery storing, the inverter translating, and the motor spinning. This integrated electrical loop contrasts with the thousands of friction-heavy, heat-wasting parts required built specifically for minimal mechanical resistance. By mastering this invisible pathway of electrons, the modern EV proves to be a smarter, quieter, and more efficient machine for the future of transportation.